Hello there. We are very happy to have you all here. And to begin the seminar, I'd like to introduce you to the Deputy Director of UCAR's Scientific Partnerships and Services Center, as well as CPAESS, Cindy Briere.
Thank you very much, Dawn. And welcome, everybody. We are absolutely delighted to have you here today at our CPAESS Discovery Seminar series. Our CPAESS scientists do absolutely everything from exploring the ocean depths, flying into hurricanes, studying the heliophysics, as well as unraveling the mysteries of the Arctic. We are super excited about all their research, and we're really excited to share this with you, our UCAR-NCAR community, as well as our colleagues at universities across the globe. So welcome again. To orientate you, at the bottom of your screen, you're going to see a Slido. We're using Slido for all the questions today, so please go ahead and post your questions. You can post them at any time during the talk. We are going to ask the questions at the end of the talk, but you are welcome to post them at any time. Today, it is my sincere pleasure to introduce you to Murali Malasala, who is a UCAR.CPAESS project scientist. And he worked at NOAA's NCEP Environmental Modeling Center. And his research looks at the improvement of weather and climate extremes, all of those floods, drought, heat waves, as well as cold waves. And he is looking at those both through a dynamical and statistical downscaling lens. And his reason for looking at these are to see how climate change will impact crop production. Today, he's going to speak of the prediction of monthly rainfall and associated extreme events over Taiwan during the monsoon season. So all please welcome Murali, and over to you, Murali.
Thank you to introduce to me, and at the same time, thank you to giving the opportunity to explore my work in the system. And my topic is prediction skill of global ensemble forecast system version 12 in depicting the monthly rainfall and associated extreme rainfall events over Taiwan during the summer monsoon season. And I am very much thankful to Dr. Vijay Talapragada and Yojan and Chen to support this study. The main motto of my study, this study is, it is well known the human-induced changes in the climate are not only increasing the global average temperature, but are also increasing the frequency, duration, and intensity of the extreme weather and climate events, such as the heat wave, cold wave, drought, flood, hurricanes, tornadoes, and thunderstorms over various parts of the globe. It is particularly noticeably more over some parts of the developing and developed countries like Taiwan and India, like that, and particularly more over the South Asia and East Asia regions. And in the recent decades, a significant increase in the global average temperature has been observed. Some of the findings indicate that the recent decades have been successfully warmer on the Earth's surface than any preceding decade since 1850. And the increased temperature in the atmosphere, it is causes to increase the water vapor content in the atmosphere, and it is leads to increase the momentous increase in the number and intensity of the heavy precipitation events. Even where it is the rainfall, it is increased, or if it is decreased, or there is no change in the total amount of rainfall. In all the places, the extreme rainfall events, it is increasing, and it is particularly more over the Asian region. The extreme rainfall events, these extreme rainfall events is the mainly responsible for the floods and the causes to widespread destruction of the infrastructure and economic damage and the loss of the lives across the world. And it is relatively high over the Asian region. And in the Asian region, Taiwan is one of the subtropical island in Asia, and it is experiences the extreme rainfall regularly and causes to landslides and flash floods in and near mountain regions and flooding over the low-lying plains, and particularly the summer monsoon season. And it is in the recent periods when we are observed the temperature increase, it is the double as compared to the northern hemisphere average. So the impact of the global warming, it is more on the Taiwan, particularly for the heat wave, cold wave, and these rainfall floods. And even it is experiences the regularly the rainfall extremes, but still it is suffers with the scarcity of the water, and due to the steep topography and hardly holds the rainwater, and it is the 18th rank of the water scarcity country of the world. So therefore, there is a demand for the understanding and monitoring and predicting the extreme weather events over Taiwan for the country's sustainability in this present global warming era. So the skillful prediction of the monthly or the extended range time scale rainfall, and it is extremes at a small regions like Taiwan. It is a challenging of the meteorological scientific community, and the existing forecast system across the world can simulate the year-to-year variation in the seasonal rainfall. However, the month-to-month variability during a year, it is still challenging. And in the recent decades, there is a lot of improvement it is there, because there is an impressive advancement in the numerical modeling and prediction of the weather and climate. Particularly in the improvement it is there, substantial improvement it is there in the short and medium range forecast or the tropical extratropical regions. But when we are compared the tropical and monsoon regions, the skill is relatively low because due to the complexity. And particularly the extended range forecast, it is challenging for the tropics and monsoon regions or for the meteorological scientific community. In the recent periods, in the recent year, in September 2020, NOAA NCAR has implemented the Global Ensemble Forecast System version 12 model to support to the stakeholders for the subseasonal forecast. Subseasonal means monthly forecast and hydrological applications. And this model data, consistent reforecast and relay analysis data, it is generated for the period of 2000 to 2019. And the reforecast data is available. It is generated with 00 UTC initial conditions for every day up to 16-day forecast with 5 ensemble members. But the forecast is extended up to 35 days with 11 members every Wednesday. In this study, I have taken for the mainly my concern is to do the performance evaluation on the monthly scale. So I have used the same model data for the weekly once initial conditions every Wednesday, because every Wednesday the forecast integration it is up to 35 days. So I have considered, and this model output it is available with 11 members, and one is control, and 10 members the contributions. And this model data it is available with it is running by 0.25 by quarter degree, but it is the stored the data it is day 1 to day 10 it is the 0.25 degree, and later on day 11 to day 35 it is the data is available for the 0.5 by 0.5. And these products are available broader community for the Amazon Web Service. And this for this study for the Taiwan, I have interpolated the data 0.5 by 0.5, because day 1 to day 11 to day 35 data is available in that resolution. That's why I have using the bilinear interpolation, and anti-data for consistency purpose I have interpolated with bilinear interpolation with 0.5 by 0.5. And here I have used as a reference data CMAR analysis data for the precipitation evolution. And these results also I have compared with the previous version GEFSv12 with the same horizontal resolution based on the weekly ones 00 UTC initial conditions. This model output also have the 11 members, the same reforecast period. Means same reforecast means it is available reforecast period up to 2016 it is there. This model data, the how many years it is available, that one I have used for the comparison. I have used as a benchmark what is the improvement in the latest this model for the prediction scale. And the major differences in both the models, both are models, it is taken from the initial condition GFS model. And the GFS sub-X, we are used for the GFS semi-Lagrangian Lagrangian and 2015 version, whereas in the GEFS version 12 used for the finite volume cubed sphere, and that is the GFS version 15 version. And physics games we are obtained from the taken from the GFS version 13 for the GFS sub-X, and whereas for the latest model, the GFS version 12, it is taken from the GFS version 15 GFS version 15 package. And initial perturbations, it is the same for the both NCAR-F06 and both the models. And model uncertainty also we are used the same like 5-scale SPPT and SKEB, both the things. But boundary forcing we are used for the GFS sub-X, it is the two-tied SST. Whereas we are used along with the two-tied and near sea surface SST also used, whereas the variability, day-to-day variability also it is accounts in the GFS version 12. And in the Argentine resolution, the GFS sub-X, it is the slightly it is lower resolution, it is the 0.5 by 0.5. And whereas the GFS version 12, it is the quarter degree. And vertical levels, it is the same in the both the models. And forecast length also it is same up to 35 days lead time it is available. And the members also it is same like 1 control and 10 perturbations. But reforecast data it is available for the GFS sub-X, it is 17 years it is there, and remaining period it is the real time it is there. And GFS version 12 have the 31 years. But the up to 2000 up to 2099 the initial conditions it is different, and we used real analysis data. The updated one CFS real analysis it is used. So for consistency purpose I have used only for the 2000 to 2019 I have used. But the performance evaluation comparison we are using the common period. And when we are talking about East Asian summer monsoon, and the East Asian summer monsoon index, it is very important, and it is just well in describing the precipitation and temperature of the East Asian region. So mainly this is how it is there. The East Asian jet stream at 200 hectopascal is an important part of the East Asian summer monsoon system, and it is influence weather and climate around the East Asia. And the East Asian jet at 200 hectopascal strongly influenced the East Asian summer monsoon. Already Dye et al. Found the summer thermal structure and winds over the Asia shows a larger thermal gradient in the upper troposphere. Large thermal gradient it is there when he studied the thermal structure and winds for the over the Asia at upper level as compared to the lower troposphere. So that means at the upper level wind, it is a bigger role for the bigger role of the in driving the East Asian summer monsoon circulation. So based on this, the Joe et al. Proposed a new East Asian summer monsoon index based on the 200 hectopascal zonal wind, which is considered wind anomalies in the East Asian region. Is taken from the three parts like 3 locations. One is the southern region, and another one is the middle and northern region. Southern means it is around is considered for the around 5 degree north, and the middle it is 20 degree north, and northern area it is considered for the 35 degree north. He is taken for the zonal wind in the 3 regions, and East Asia means he is considered for the longitude 104 degree east to 140 east. Plus or minus 2.5 means around 5 degrees centigrade, 2.5 to 10 degrees north. Box it is taken for the southern region. In the middle region 17.5 to 22.5, and same longitude 105 to that box area average it is taking. Like that, the zonal wind considered to calculate the East Asian summer monsoon index. We can see here it is eastern, southern and northern area it is the easterly, and middle it is the westerlies. And here is taken as a normalized after calculating the anomalies, and is doing the normalization, and the normalization time series, it is used as a East Asian Summer Monsoon Index. And during the, suppose the East Asian Summer Monsoon Index, it is the positive. That means the East Asian Summer Monsoon system, it is very strong. And during that time, the easterly anomalies appear around 5 degree north, around 20 degree north. And whereas the westerly anomalies appear around the 5 degree and means the south and northern part, 5 degrees and 35 degrees north. And this East Asian Summer Monsoon Index is a good at describing the precipitation and temperature variations for the East Asia. And also the East Asian Summer Monsoon Index closely associated with the East Asian and Pacific or the Pacific-Japan teleconnections. And it is also possible role for the internal dynamics to East Asian Summer Monsoon variability. And it is also significantly linking with the ENSO and tropical Indian Ocean SST anomalies. So, there is a strong link with the East Asian Summer Monsoon Index and East Asian Summer Monsoon system. So, before going to evaluate the model, it is need to know how the model is performed in depicting the East Asian Summer Monsoon. So, in this study, first I have evaluated the performance evaluation of the GEFSv12 sub-X and the GEFSv version 12. Day 1 to day 35 forecast for the East Asian Summer Monsoon Index. Against, I have used as a reference year for index calculation NOAA NCEP GEFSv version 12 real analysis data for the same period. And those index from the both the models are evaluated against the NOAA NCEP GEFS real analysis using standard skill matrix. And also in this study, I have after that I have used it for the calibration. It is well known. We are taking any raw model product. It is rarely used because it is exhibit the systematic errors and the bias mainly due to the spatial resolution, limited to the spatial resolution and simplified physics and thermodynamic process and numerical schemes, incomplete understanding of the climate system process. Also, when we are looking for the errors in the GCM simulations, it is large when we are compared with the historical observations. It is already proved. So, any raw model output you can take in, and it is rarely used because of this systematic errors. So, it is very important to do the bias correct the raw model output in order to produce a better weather and climate forecast with the different time scales for climate risk management in various sectors such as the agriculture, hydrology, health, like. And it is well known that particularly the bias correction methods, the traditional mean bias method, it is there. It is only works for the non-stochastic variables like temperature, but it won't work for the more sophisticated approach, more sophisticated variables like rainfall. So more sophisticated approach, it is bias correcting method, it is needed for the correcting the bias, because the model also, most of the models have the drizzling problem. Means too many low magnitude rainfall events it is there when we are compared with the observation. So the quantile mapping method is one of the most important and popular bias correction method to apply the correct the bias in the regional climate models, the model simulations as compared to the model data. So in this study, we are applied the quantile mapping method, and this technique is mainly used to correct the model predicted rainfall distribution and mapping into the observed rainfall distribution. Also, this method simply you can call like histogram equilibrimation or rank matching method. The rainfall intensity distribution from observation and model forecast in this study well approximated, gamma distribution approximated, and we are using the empirical probability distribution. Rainfall values has been used in this technique. The calibrated output in this inverse technique is the inverse of the CDF of the observed values at a corresponding to the model CDF at the particular value. Suppose you know the model CDF and observed CDF, then you can correct the the particular time forecast by using this both. It is like observed inverse of the observed CDF into forecast reforecast data long term CDF into the particular day forecast value you can correct by using this. And this technique simply you can tell it is the transformation between the two CDF from the model to observation. This calibration method applied, how I applied in this study, I applied in the each member it is separately. Also, I have applied ensemble mean of the 11 members separately, and each grid point and each lead time separately I have applied. For example, in this study, I have studied in the monthly scale. So I have used the model output, it is available for the weekly case. So exact June 1st to June 30th, you cannot get. So I have used the forecast from the 16th May to 15th June for the June analysis purpose. So almost 4 weeks or 4 to 5 forecasts for coming for the year. So total 20 years period, I will get, I am getting 89 forecast for the June case. So the 89 forecast I have used to for the calibration of the monthly forecast, and in this study particularly I have used leave-one-out cross validation. Suppose one initial conditions monthly forecast I want to correct. So in that case, I have used the remaining all the periods for the estimate the CDF for both the model and observation, and use it to correct this particular initial condition forecast for the particular lead time. Like that, I have done for the all the lead time for all the members separately. In the same practice, I have applied for the other months, July and August and September analysis. And this is the one of the example you can see. This is before applying for the calibration method. You can see the observed rainfall and predicted rainfall probability. Suppose you can see the around 55 or 59 probability 0.55. In the same probability, you can see observed rainfall. It is intensity. It is more than 6 centimeters, 6 millimeters. But where we have seen the in the model, it is less than 5 mm. That means the low intensity rainfall events probability, it is high in the model as compared to the observation. So some drizzle problem it is there here, that problem it is there. Particularly this model, it is this calibration method, it is corrected to that distribution. And some of the preliminary results I have explained in this study. Firstly, I want to tell the performance evaluation of the GEFSv12 version 12 and GEFSv12 model in describing the depicting the East Asian Summer Monsoon Index. So some of the skill scores I have displayed here. This is the first one is the root mean square error. These skill scores it is done for the each lead time separately, and each model against the NOAA NCEP GFS version 12 real analysis against. Then you can see here the error is the RMS error is for the in depicting the East Asian Summer Monsoon Index, it is less in the shorter lead times, and it is increasing with the lead time. It is increasing. But when we are compared among the between the models, the GEFSv12 model have the less error, and slightly less error it is there for the shorter lead times. And when you are going for the longer lead times, the reduction in the RMSE it is more. So the improvement particularly it is there for the longer lead time forecast. Forecast in the longer lead time forecast. And when we are looking for correlation coefficient, the correlation coefficient of in depicting the East Asian Summer Monsoon Index, it is good from the both the models. It is more than 0.65 for all the forecast lead times. However, it is decreasing with the lead time. At shorter lead times, day 1 and day 2, it is around 0.8. It is there from the both the models. But when we are compared with the in between the models, it is marginal improvement can be observed from the GFS version 12 for the shorter lead times, but large improvement, remarkable improvement, it is there for the larger lead time forecast. And in the similar way, you can see for the index of agreement, index of agreement also it is good for the both the models. It is almost for all the forecast lead time, it is greater than 0.8. 0.8 means it is a good scale relatively. And in the shorter lead times, it is around 0.9. It is there from the both, but some marginal improvement it is there from the updated version GEFSv version 12. But the remarkable improvement it is there for the longer lead time forecast. And this is for the index purpose. And also I have calculated the taken from the over the Taiwan region and rainfall, how the improvement it is there in the GFS version 12 as compared to the GFS sub-X. So here I have overall performance I have performed here day 1 to day 35. And the first one is the climatological mean from the both the models and CMORPH. The CMORPH around 8 mm it is there per day, millimeter per day, but both the models it is large wet bias it is there. Large wet bias it is there, both the models for all the forecast lead times. And slightly it is the wet bias it is reduced in the updated version, updated model GFS version 12 as compared to the sub-X. And in case of standard deviation inter-annual variability, it is more in the observation, but the inter-annual variability it is underestimated in the model. But even in the shorter lead times, it is okay up to it is capturing something. But with the lead time, the inter-annual variability it is decreasing in the both the models. But when we are compared with the models, the updated version, yeah, it is relatively better in depicting the inter-annual variability, represent the inter-annual variability. And in case of coefficient of variation, also similar pattern can be observed, and it is a large underestimation it is there in the both the models, but a slight improvement can be observed from the updated version. In case of spread, the spread is less for the shorter lead times from the both the models, and it is increasing with the lead time for the spread is increasing with the lead time for both the models. And in the shorter lead time, the spread is less in the updated version as compared to the sub-X, but longer lead times, the spread is increasing in the updated version. And these are the statistical skill scores like mean bias and root mean square error, and correlation coefficient and index of agreement from the raw and this is the raw and quantile mapping method. Sorry, this is the this is the sub-X and updated version. Here, these skill scores also, before I explain a previous slide, the similar things you can observe. The marginal improvement can be observed from the updated version, GFS version 12. Yeah, but both the models have large warm bias, it is there, wet bias, it is there, and yeah. Then this is for the some probabilistic ensemble probabilistic skill score comparison between the sub-X and updated version version 12. And we can see the both the models here, that wet and year days, how I consider if it is the particular day rainfall greater than 2.5 mm, then I have considered for the wet day. If it is the more than 5 centimeter rainfall per day, that is have considered like it is extreme rainfall day. So here I have calculated the skill scores for both separately, wet days and year events, extreme rainfall events. And we can see in the both the models, as compared to the reference forecast, it is better because both the models, the curves, it is shows the above the diagonal line, and it is good in the both the cases. In that case, as compared to the reference forecast. And we can see in this case the improvement, the marginal improvement can be observed from the updated version GFS version 12 as compared to the sub-X for the wet days all the months, and June, July, and August and September, both the cases, both the models. But some marginal improvement can be observed. And in case of the extreme rainfall events, the improvement it is more for the version 12 model as compared to the GFS. The improvement particularly it is more for all the months. And this is the climatological mean. And now because the major improvement in this GFS version 12, it is the updated physics, advanced physics. Also the resolution also it is there. And the finite volume core sphere, that is also maybe that is also one of the reason to improve the skill as compared to the subjects. And this is now I have applied for the quantile mapping method on the GFS version 12 model. And this is the performance evaluation of the raw model output and calibrated forecast. The first row it is indicated the observation, means CMOF. The spatial pattern of the rainfall, it is indicate that the most of the rainfall it is occurred over the southern regions and eastern part, and it is decreases towards south to north and east to west. The similar patterns can be observed from the raw model product for all the months, but when we are compared with the observation, large wet bias it is there in the model. Particularly in the south and eastern region also it is there. Most of the grid points it is there. But after calibration, the overestimation or the wet bias, it is remarkably reduced in most part of the Taiwan, and the spatial patterns, it is very similar to the observation for all the months. And this is the inter-annual variability of the monthly rainfall and June and July and August, September. And from the observation, you can see the inter-annual variability, it is particularly more over the south and eastern parts, where is the prominent rainfall it is occurred. And in the raw model product, the inter-annual variability it is less as compared to the observation, but it is slightly in the southern part. It is overestimation in the during the July month. But after calibration, the large underestimation of the inter-annual variability, it is improved in the calibration method, but it is slightly overestimation it is there. And the coefficient of variation, we can see it is a reverse pattern to the climatological mean and inter-annual variability of the monthly rainfall. And the similar patterns can be observed from the raw model product also, but it is limited in capturing the magnitude values, But after calibration, the spatial pattern of the coefficient of variation, it is very similar to the observation. But in the September case, some of them, it is a slight overestimation it is there, like inter-annual variability, that overestimation. Sorry. And these are the some statistical skill scores for the raw model product and calibrated forecast against the CMOF. And the root mean square error, it is large in all the monthly forecast. You can see particularly the RMS is more for the southern region and the eastern part, and it is decreases to south to north and west to east, east to west, like climatological mean pattern. That means where is the prominent rainfall it is occurred, those regions, the RMS also it is more. And the root mean square error, particularly it is more for the July case. July it is more. But after calibration, the root mean square error it is decreased. It is decreased slightly, some part, but some months it is slightly it is increased also it is observed. But when we are looking for the climatological mean bias, it is almost it is nullified, but it is slightly wet bias it is there. But it is when we are compared in the raw model product in June case, it is 87 mm for the month, but after calibration it is coming to the 1.2 like that. It is almost reduced, remarkably reduced. And this is the index of agreement. The raw model itself, it is the good in index of agreement, but the low skill can be observed for the eastern part. Eastern part it is there. For the particularly it is low for the July case. It is there. And western part it is particularly it is more agreement it is there. But after calibration, it is slight improvement can be observed for the all the months forecast. It is like 0.62 in September case, it is improved 0.62, and August case 0.59 to 0.62. Like that, marginal improvement can be observed in the calibration method. And this is the CDF plot, I have pulling all the grid points for the July, and you can see here, this is the CDF cumulative distribution function CDF, and we can see the red one here. The red one is the raw model product, and green is the calibrated one, and black one is the observation. We can see in the June case, almost it is very less probability it is there for the dry days, and even it is not more than 10% is also there, less than 10% of the days, dry days it is there, less than 10%. While in the observation, it is almost 50% of the days, it is the dry days it is there. That means model have a large low intensity rainfall events it shows, and at the same time, you can see the extreme rainfall event case around 6 centimeters. The curve is almost saturated. It is reached to the 100%. So that means it is able to predict the extreme rainfall events. But after calibration, the distribution it is improved a lot. It is improved a lot, but it is not same as the observation, but it is very close to the observation. The similar thing can be observed for the July case and August and September, but the improvement particularly more for the September and June. 3 months it is there, but the improvement is less for the July case. July case still it is a lot of gap it is there. And this is for the spatial distribution of the wet days from the observation and raw model product and calibrated. Here I have actually the calibration method I have applied each individual member and also ensemble mean. And here I want to know, suppose we are considered for the ensemble mean and how it is represented for the wet days and extreme rainfall events. If I have considered, I have done consider for the each member separately and identify the wet days and year days, and then I have done the mean. How it is difference it is there, I want to know that, and I have done that. The first row it is the first row and left side plot, it is the for the wet days. And you can see observation wise the wet days it is the particularly it is more for the south and eastern part where is the prominent rainfall it is occurred, and it is decreased towards north and east to west. And the same like climatological mean pattern of the rainfall, monthly rainfall. The similar pattern can be observed from the raw model product also, but you can see almost most of the days it shows the some rainfall more than 2.5 rainfall because of the drizzle problem, and because of that large our estimation of the wet days can be observed here when we are considered for the ensemble mean ensemble mean. But in the I have identified the each member separately first, then I have done the mean. Then in that case, the number of wet days it is less as compared to the ensemble mean case. That means our estimation is less as compared to this. But even still, even we are consider individual members, the our estimation can be found as compared to the observation. But after calibration, individual member and ensemble mean, the spatial pattern of the wet days it is improved a lot. It is improved a lot, and yeah, even each individual members also it is improved a lot. And but each individual member slightly our estimation can be found. Our estimation, slight our estimation it is found, but in both cases it is improved. And in case of the extreme rainfall case, and in the extreme rainfall case, raw model product, it is a large underestimation it is there. But when we are considered for the ensemble mean, but when we are considered for the, we are identify the extreme rainfall events each individual member separately and then take the mean. In that case, the at least it shows some events. So when we are taking the mean, the peaks will be smooth out. So that's why it is missing. And at the same time, even some dry days it is missing. That's why wet days it is coming, more wet days it is coming. But after calibration, the spatial pattern of the extreme rainfall events it is improved. It is particularly the improvement can be seen for the even ensemble mean forecast and individual members also. And individual members case, yeah, in the both the case it is there, but somehow it is our estimation some months slightly, and somehow underestimation it is there in the individual member case. And this is the ATS equitable thread score for the wet and year events. In the raw model product and ensemble mean case and individual member case, you can compare when it is the large over estimation of the wet days it is there, and at the same time the ETS also low for those cases. But when we are compared with the individual, when we are considered for the individual members separately, then mean in that case the our estimation of the wet days it is less, and ETS also it is more. It is more as compared to. But after calibration in the both the cases, it is improved a lot for the all most of the grid points for all the months. And in case of the extreme rainfall events, in the similar pattern can be seen actually in this case. As compared to the wet days, the ETS is more for the extreme rainfall events due to the underestimation. The overestimation it is not there, and underestimation particularly it is there slightly. But when compared with the ensemble mean, the individual members mean, it is better. But after calibration, when we are compared in between individual members and ensemble mean, the ensemble mean it is outperform than the individual members mean. And the performance diagram, I have also done some performance evaluation to depict all the statistical categorical skill scores like thread score and success ratio and probability of detection and mean frequency bias. This is a defect to all the 4 skill scores. And this is suppose it is in this bottom line, that means here it is there, then that means it is the worst. If it is the top corner this side, and then it is the better performance. But in this case, I have done ensemble mean case. I have considered for all the 4 months in the raw model product and calibrated forecast. In the raw model product, you can see it is far away from the diagonal line. If it is it shows on the along the diagonal line, that means the model is able to produce the same number of events as observation has observation. So here the model have the ensemble mean model have the all the 4 months have the large overestimation it is there. So that's why the index hit rate is more, but large overestimation it is there, and the success ratio it is less because the false alarm rate it is more, and the thread score also it is less as compared to. And but after calibration, the overestimation it is remarkably reduced. It is near to the diagonal line, and day 1 forecast it is almost 100% it is able to produce, and at the same time remaining 2 months, sorry, this is the June case it is near to the 100% produced, and even June, July, August also it is 90% of the events it is produced, and the hit rate also it is more than 0.7, and even a thread score critical index also it is around 0.7 it is there. And success ratio also it is improved a lot, because the success ratio improvement it is due to the it is a reduction in the false alarm rate. False alarm rate it is decreased. So that's why the improvement can be observed. The similar thing can be observed for the extreme rainfall event case. In the extreme rainfall event case, the ensemble may have the large underestimation. It is the lower side. That's why hit rate also it is less, and success ratio it is more. But after calibration, it is the large underestimation it is reduced, and it is able to produce some of the the extreme rainfall events. But a slight overestimation it is there. It is above the diagonal line, so slight overestimation it is there. And at the same time, it is increasing the hit rate also it is increased, and the thread score also it is increased. ETS also it is increased. So the calibration method it is improvement it is there. It is improved, remarkably improved the both the events. And this is for the individual members case. I have considered for the individual member case. In the individual members case, it is even individual member case also it is overestimation it is there, but after calibration it is the overestimation it is decreased for the wet days case, and it is very near to the diagonal line, and it is improved particularly for the success ratio it is improved, and thread score also it is improved. In case of the extreme rainfall case, June and July is the extreme rainfall case, it is the overestimation individual when we are considered for the individual member, and August and September case it is the underestimation it is there, but anyway it is near to the diagonal line. But after calibration in the all the 4 months it is very near to the diagonal line, diagonal, a lot of improvement it is there. And some of them PDF hit rate also it is improved for the August and September. And yeah, thread score also it is improved. Some improvement it is there in the case of this, but clear picture can be observed for the improvement for the ensemble mean case. Yeah, the categorical skill scores and some other statistical skill scores, it is enabled to reflect the uncertainty of the model for the ensemble probabilistic forecast. So that's why the probabilistic ensemble forecast skill scores can be represent to understand the uncertainty in the model and the calibrated forecast. So here I have calculated the Breyer score for the wet days and also extreme rainfall event case. If it is the Breyer score, it is 0. That means it is the good. If it is the near to 1, that means worse. So in the case of you can see here raw model product, the Breyer score it is more the Breyer score value it is the more over the eastern region, and it is decreases towards west, and that means it is the skill is low. That means the Breyer scale, the performance is low for the eastern region, and but after calibration the skill it is improved lot. The skill is improved lot. It is decreased. It is the value is decreased. That means improvement it is there. And the similar thing can be observed for the extreme rainfall case. But when we are compared with the Breyer scores, it is for the wet days and extreme rainfall case. Extreme rainfall case, the values are very near to the 0. That means the errors, the Breyer score, based on the Breyer score, the performance is good for the extreme rainfall case, because the errors, the overestimation is less, and that's why it is so. And in case of, I have also calculated the reliability of the probabilistic ensemble forecast for the wet and ER events or Taiwan. And in this case, you can see in the reliability means if it is the 0 value means it is good reliability. If it is the near to the 1, that means the reliability it is the worst. So here the green one is the near to 0 and red one is the more than that. And we can see for all the, in all the cases, it is actually it is the reliability it is good, because in both the model case it is less than 0.1 for the wet days in June case. But when compared among the between both the method calibrated and raw model product, the raw model calibrated forecast calibration method is marginally improve the reliability for all the forecast lead times. Even you can see for the July also can be observed, and August and September also can be seen. So the same reliability improvement it is can be observed for the rainfall forecast, rainfall case, but the improvement, the reliability is already more for the extreme rainfall case, but the improvement as compared to the is less as compared to the wet days case. But in both the cases, reliability is more for the when compared with the wet days, because a lot of overestimation it is there in the wet days. That's why yeah, that's why the reliability is less as compared to this. But the improvement, marginal improvement can be observed for the both the cases. And this is for the ROC curve. The ROC curve is the good indicator to the how it is performing as compared to the reference forecast or climatological forecast, the raw model and calibrated forecast. Both the cases, it is improve. It is the better than the reference forecast or climatological forecast, calibrated and raw model product also. But the calibrated forecast can be seen the calibrated method it is marginally improved the area under curve. You can see the area under curve for the raw model product for the June case wet days it is 0.63, while it is the calibrated method it is 0.64. Slight improvement it is there. Even extreme rainfall, the improvement it is more particularly for the extreme rainfall case. You can see the raw model area under curve it is 0.61, and but after calibration it is improved 0.65, means almost 0.04 it is improvement it is there. In the similar thing can be observed for the other months also, the improvement can be observed for the, but while we are compared with the wet and extreme rainfall events, the extreme rainfall events case the improvement it is more, but marginal improvement can be observed after calibration for the particularly for the extreme rainfall case, extreme and wet days. This paper is published in American Meteorological Society and Journal of Weather and Forecasting. These are my summary and conclusion. My conclusion is there is a remarkable improvement in the updated version, means the global ensemble forecast system version 12 model as compared to the global ensemble forecast system sub-X. These improvements may be attributed to the combined influence of the better initial conditions and more advanced microphysics schemes and finer resolution and a new finite volume dynamical core. These are the reasons. Maybe these are the reasons to the marginal improvement in the this global ensemble forecast system version 12 model as compared to the sub-X. And when we are looking for climatological features from this model, is able to represent the climatological mean, interannual variability, and coefficient of variation of monthly rainfall for Taiwan during summer season. However, it has a large, remarkable overestimation, large overestimation for the mean and interannual variability of the monthly rainfall, and it is particularly more during the peak monsoon season like June and August. After calibration, the overestimation of the climatological mean and interannual variability it is reduced remarkably, and the skill scores are decreased with lead time, and the RMS and mean bias errors from the monthly scale is high in the south and eastern part where is the prominent rainfall occur, where and but the errors of the RMS and mean bias decreases south to north and east to west during all the months, but after calibration the errors notably decrease for all the months. The prediction skill also it is good in raw model product, and but some marginal improvement, remarkable improvement can be observed after calibration in the even correlation coefficient and index of agreement. Correlation coefficient it is the improvement is less, but index of agreement it is improved a lot for all the months. There is a considerable overestimation of the wet days most part of Taiwan from the raw model product for all the months, but after particularly whereas the underestimation can be observed for the extreme rainfall case, but after calibration the overestimation of the wet days and underestimation it is reduced. The bias is reduced, and it is well distributed in the both the cases. Relatively well distributed both the cases by using the calibration method. And the calibration method significantly improve the most of the statistical categorical skill score like frequency bias and accuracy and false alarm rate. These are, but wet days also. But we can see a reduction in the hit rate for the wet days because it is already overestimation for the wet days. When you are calibrated, automatically it is reduced the overestimation. Then POD also it will be reduced. So that is there. And the assessment of the probabilistic forecast available that there is a marginal improvement can be found by using the calibration method for the both the cases wet and ER events for Taiwan for all the summer months and after calibration. Thank you.
Thank you very much, Murali. That was fascinating. I really enjoyed it. Thank you for sharing your science with us.
Yeah.
I want to let everybody know and direct you back to the Slido. You can scan the QR code on the screen right now, or you can go to the bottom of this presentation to enter your questions. And while you do that, and before we move over to the questions, I do want to invite you to our next seminar. Our next seminar is going to be on May 24th, and that would be Malasala Ulad. She's a project scientist working with the Naval Research Laboratory. Thank you very much.
Thank you.
Okay, so it looks like our first question is, could you expand on why you picked the QQ for the bias correct method? And have you tested other methods before you picked this method?
Yeah, I have compared with some other methods also, but when compared with other methods, the quantile mapping method, it is good in particularly improve the skill for the extreme rainfall case. The mean bias and other methods, it is Mean by it is reduced, but multilinear regression, some other methods, but the quantile mapping method, it is good in the distribution of the various intensity rainfall events.
Thank you. And we have another question. If I missed it, did you include any parameterization on raindrop size and AOD? How did these affect the model performances during extreme events?
Is telling about the aerosols. Can you repeat once?
Sure. It says, if you missed it, did you include any parameterization on raindrop size and AOD? How did this affect the
aerosols optical depth? Yeah, latest models in the NOAA, it is also included the those things, and we are doing the performance of that after including the aerosols, this component also. Maybe some improvement, maybe it is there. Up to now, I didn't done, but I am going to do that. I will see the comparison with that.
Okay, excellent. Then we have another question. Have you tested this for other regions? And if not, are you planning to do so?
Yeah, I have tested with our Indian region already. That paper also is published, and but it is not in monthly scale. It is the day 1 to day 16 lead wise I have done, and there also I have found the model particularly have the large low intensity rainfall events, and that will be improved by using this method. And also it is improved for the extreme rainfall case for all the forecast lead times for Indian monsoon.
Okay, and then this one says, what improvements to the current models would you like to see incorporated to further enhance prediction ability?
Yeah, right now I am also applying for some machine learning methods, some hybrid post-processing methods, and already it is in the revision, it is in the review with the Artificial Intelligence Journal Access System Science in American Meteorological Society. So we are also applying some other methods like combination with the artificial neural network with some quantile mapping, some other methods. Yeah, new approach to particularly improve the extreme rainfall events, because the quantile mapping method, it is able to produce, but it won't be improve the correlation coefficient. So at the same time, it is need to improve the correlation coefficient and iterate and those things. So some combination with this method, it is necessary, and I am working on that.
Okay, thank you so much, Murali. It looks like that's all the questions we have right now.
Okay. Please, if anybody any questions, and please mail me and I can answer.
Okay. Well, I guess we would, CPAESS would like very much to thank you all for coming to the UCAR CPAESS Discovery Seminar, and remind you to go to our website to find out about future talks at cpaess.ucar.edu. And you're also going to be able to find a link to this talk after it's been uploaded onto YouTube this week, in case you want to go through it again. And Murali, our sincere thanks to you for sharing this important research with us. Thank you also to Brett Batterman of UCAR Multimedia Services for his invaluable assistance. And we hope to see you all on Wednesday, May 24th for our next talk. Thank you.
Thank you. Thank you. Thank you so much.